of LVMB-manifolds.
Yeah, on the generalization. Okay. So thank you to the organizers for giving me the opportunity to look in this email conference. This is my first time that I participated to such a fully female speaker event. So I could not decline. I feel I could not decline. Okay, so, but at least this is my second time in Sofia. So the first time I was a guest of Valdemar, and I am very pleased to be back here with another topic. And I hope this topic is really nice for some people here. I mean, working here. So I hope so. Let's beyond this group. Let's see what I mean. So what as the title sounds, I will outline a construction, actually a quotient construction of complex manifolds, which will be compact and non-Keller. So we have seen already many actually several talks on the complex manifolds, but I would like to motivate a bit why one should be interested by non-Keller, and I know that people here may not know, sorry, with no offense, what Keller means. So let me just make a brief drawing. So you have the complex manifolds, let's see here. Okay, so as in the previous course, so wave manifold with a complex structure, and you have smooth manifold with a nice two forms, so-called symplectic form, the so-called symplectic manifolds. And whenever these two structures, so here you live in the smooth world, these manifolds at least, using the smooth are smooth manifolds. And whenever these smooth manifolds carry these two structures with some compatibility condition is called the Keller. Maybe it is very deep. But there is no criterion to detect when so there are two approaches. Either you start with the complex manifold and you ask for a symplectic structure which is compatible with a given complex structure, or you may come from the symplectic world and ask for a complex structure which is compatible with a given symplectic structure. But there is no criterion. But for this, there are some sufficient conditions to say yes or no, but there is no criterion. So there is a sufficient condition when known, as we was displayed in the last slide, telling us something on the homology. Let's say the homological condition. So to understand Keller manifold, you can put change your mindset and say, okay, do we understand non-Keller manifold? This is what I would like to address today. So from the perspective of okay, so this is what I wanted to say. So the most famous example, maybe the most famous of the pioneer examples of the complex manifold which is not Keller, which is not Keller. I am tired. I'm very sorry. Of manifolds. So what is it? So it's a very simple object. So as I say, I will realize this manifold as quotient, so meaning that I have an action. Okay. So here, in the case of a log manifold, you consider Cn, this Cn, acted on by an infinite cyclic flow. That's not there. This is the cycle group generated by a complex number G. It's called Bosor is isomorphic to Z, but it is important to keep in mind what G is. And here you ask about complex numbers. Complex number. Non-zero, and also use value different thing at one. So you are just by scaling, okay, so this is the complex number, you ask by scaling of this interval, and you consider the orbit center of the whole CM, but just of the particle. Okay, and you get a quotient just as a log test. And this is what you call a log manifold. And the fact, general fact, by this cohomological sufficient condition that has been alluded to, I mean, there is no simply, so this is a complex manifold for the very simple reason that this is a quotient given by an action which is free, and it's compact if the action is not really discontinuous. This is the called Bob manifold. I won't want it. The second part manifold. And it is not given. Even stronger. Why? Because there is no two form. In the case when n is not one. In the case when n is one, this is a elliptic curve, so it is indeed. Because there is no two forms, this is diplomorphic to two copies of the sphere. So this is why not you can even do eventual activity. Was it? It's not very, it is really well known, not exaggerating when saying this. So we would like to generalize this construction. So there were some generalization of this construction, the so-called LVMB-manifolds. We have been studied here by people here. This is an acronym for sorry, Lopez de Medrano. Bergowski, Merseman, and Bousio. You may wonder why not alphabetical orders. This is a chronological order. So this construction was first generalized by Lopez de Medrano and Bergowski, then by Merseman, and it culminates in the construction of Bousio, the way I will present. Okay. So which actions are we considering here? So you have again, as before, consider this confined space, Cn. So this group was complete, so you drop this abstraction, but you keep on with the Abelian group, Cn, Abelian. We find out that an action à la Bousio, and see that we present the most general construction. So here you have an n-tuple of complex number, n-tuple of complex number. And these are given by, this action is given by prescribing some linear forms as much as the dimension of the manifold where your group is acting. You are given n1, given n linear forms. Cn. This linear form may be equal, don't require this linear form to be pairwise difference. They may be, there may not be. There is no further assumption, any n-tuple of linear forms. Some of them may be equal. There is really no further assumption. And whenever you are given this n linear forms, consider the exponential of these complex numbers, around d, s1, and so on. So the action, you cannot, it's really simple. Okay. Because it's a general, I will have any times. Not by B, because I will, B for me is already taken, the representation theories, already for all, I suppose. Par Bosio, but I will have this stuff, action as label. Okay, so this is an action, it is not algebraic, and because of this exponential. Let's see. Okay, so now the theorem, so I will review how to build on these actions or quotients, which are compact complex manifolds, which are not linear. This is the theorem I will formulate, as I said, in the very last generalization. So it is done, it is done Bosio, but I will not formulate it as Bosio did it, so it is already classified as we go. But as a combination of the reinterpretation of this, I mean, not a reinterpretation, sorry, a reformulation of it by Battisti. So, it was a moment 10, I'm sorry. This is okay, in this very Battisti. So I will not be very precise of the statement, at least. What are we doing here? So we will have, so if you take the whole quotient, the whole of states, I mean, no chance this to be a complex manifold. Okay. So this is how, like, I don't know if you are aware of geometric enlargement theory, but once you want to build, to have a quotient with a nice quotient, usually you don't take the, you don't perform the quotient on the whole set, but open subset of it, as you did here. I mean, this gamma D is very gamma D acts on the whole Cn, and you drop the zero. So this is an open subset from Cn on which you have gamma D does not have the on the zero of Cn. Okay, so let me formulate this in this way. Okay, so as I said, this gives you Bosio gives us a characterization of all the open subsets of the Cn, which are stable on this action because we want to take an orbit space for sure. So we just want to this. Is that when you take the orbit space, it is a complex manifold and it is compact. Okay. So on this set, it can be, I mean, understood. So I have to tell you, okay, so there are many ways of describing subset, but Bosio described this set by giving you the coordinates. And this is really a coordinate formulation. The coordinate of the element of Cn should not be 0, and because of this, in the same sense, to this L, to this linear form, this can be purely formulated in a purely geometric combinatorial way regarding this index thing. Okay. So this I will not tell you, but exactly so I will formulate it. But it's still as that is deep, there exists a pair of data, calligraphic F and N. So where's F? So N is a quasi-lattice or finitely, let's say, generated abelian group. F is what we call a span, and this span is supported on N. You have your finitely generated group, so be aware, not necessarily a lattice, I will come back to it, not a lattice in the way that we saw yesterday, a lattice in the sense of a discrete group. Yeah, this may be, but that is the way I know it. And the fun is a bunch, is a nice configuration of polyhedral groups. So here I don't know if you are, you know about toric geometry. This appeals to toric geometry, but in the generalization, because in toric geometry, these files are supported on lattices. So here you drop this assumption of being a discrete group, taking an efficient abelian group, and sometimes with class configuration to of codes. And this U, and you take U to be to this file that you can associate with it. This was this one. We want any U, so this is a purely combinatorial way, so I did not tell you exactly how this goes. But anyways, you have the combinatorial characterization in terms of the vanish of the index of the coordinates which should vanish and they should satisfy some combinatorial properties. Bozo formulated this theorem in terms of the very LJ, not passing through the line. And I think this was very clever from Laurent Battisti, that actually it appeals to a well-known object in toric geometry, generalization and toric geometry, and even the picture itself really nice because you see 5 here, that's region 2. If you look at both your condition, you will have some condition like this. Myself, I cannot understand that. I cannot see it. Anyway, so you have this toric language, let's say, generalization of the toric language from the discrete case to the non-discrete case, lattices, not necessarily lattices.
Sorry, I have a nice question. So you take any finitely generative building group, or
Sorry?
the end that you're taking any finitely generative building group? Or
Okay, so sorry, I didn't get any finite, no, but you have to assume something. Thank you for the question. So M should be bigger than any finitely. CM is CM as a Lie group, as an abelian Lie group. The bracket is trivial. CM is a complex Lie group. Okay, so now I would like to mention maybe the observation here, key observation. About the theorem. So I mentioned the historic case. So this was an old observation by Dan Zafran and myself, and we were postdocs, so long ago. Okay. So as I said here, you take any linear forms of CM, meaning n tuple of complex numbers. So now when you consider the rational case, meaning that all the LGs are rational, they live in Q are rational, so which was not supposed, which was not supposed to. So if then the picture is like this. You have your mu, you have, okay, sorry, I can say this manifolds are called LVM manifolds. LVM. More or less, we have from the title of the section. So you have your LVM manifolds. And whenever all these LJs are rational, you even we prove, this was an observation, as in mathematics in general, this is the proof which is most important, is the idea of the statement. This was here, I mean, most of the idea, because once the proof was really straightforward, but because this white I wrote this circumstance, and it's an observation. We can solve this here, in this case, there exists an embedding as the group of Cn so this Cn is a complex early group into an algebraic group, an algebraic torus, power of C star. This is a complexity group. This is a complexity group of C star algebraic. So that this subgroup Cn into this algebraic group is closed and co-compact. And that the Cn action, the star action, is actually the restriction of an algebraic action of this algebraic torus onto C. So this things which scare me because I come from evidence for algebraic geometry, even geometric representation theory. I don't like this connection, general, algebraic, so this, oh my God. But then I was trying to, but it reminded me something I know from toric geometry, and indeed, in this case, it is this action, which is weird from algebraic people, it's just a restriction onto a non-algebraic group of a very algebraic action. And so here, and that actually, even not only it is Cn stable, so that you can perform the quotient, but it is even stable on this algebraic action. So here you do have quotient with a nice structure, and this nice structure is that this is now an algebraic variety and even a toric variety, which is called maybe projective or only complete means compact with the algebraic case. And this actually observation came before Battisti result. And this based, and we have some conjecture on this, and Battisti solved one of our conjecture. So this it exists on this one. There was this idea of Battisti of having the fund is component. Okay. So now I cannot explain everything. So I started when the start. So I have to finish at yes. So I can say more things of, but I will be a bit sketchy on that. No, I think I still have time. So I need this blackboard. Erase this. And if you know a bit of toric geometry, I mean, you have some nice algebraic variety acted on by an algebraic torus. Okay, so you have, and you want to describe the geometrical properties of your even toric variety, and then this span structure gives you a dictionary between the combinatories and the geometry. And here you have the same. So this span actually not any span because you want to have compactness. Sorry. So you have, so here you can even add that the span table it means to be complete. So it covers. It supports cover. So this could be a pad, only one pole. You don't want this. You want that to cover the whole ambient end in this sense. And you want to have here smoothness. So you have to add think about the fan. You don't demand the toric variety to be here smooth. We can this property just simply share the family. So all the code of the family solution. This you can add. And if you don't know the dictionary, just forget this. But since I am recorded, I better not to put too many things under the work. Okay, so this I have this nice picture. So now I do have the just quotient back here and the fibers. So you have the fibration of the LVMB of the complex manifold, which is not algebraic, with a base, an algebraic variability, and the fibration is given by compactor, text compactor. So not algebraic. Not that fast, it's a compactor. Okay. And when this is not, so now from the second observation, so this for this not I would say that this is an observation also. Maybe upset at this, but whenever you drop this condition of the rational, so any LJ, rational, so any LJ in the Boson case, you have what some people call quantum torides. So the terminology here, people do not agree, but I will keep forward. So look at people here. So you still have two of them, Verjovsky and Merseman. And you have Korsakoff and Lucasio. Like I was saying, I will do something hybrid here beyond this group. And these are, as they call the quantum torides. There is no more here algebra, structure of an algebraic variety, but the structure of an analytic stack. So this is what you have. And these people have developed a big theory on, generalizing the toric geometry in the case when this, are not anymore varieties, but analytics. The theory which really extends the toric geometry to the for five supported, for five not necessarily supported on lattices. Okay, so this we are. So now, as I said, I have a geometric representation theories for me available as I will be boring. So I would like to bring more symmetry in the picture. So what I could observe is that actually on the nice book of one of my professors, who passed away, Dimitri Akesov, in one of these books, well, like this exercise on Hopf manifolds, they use that actually surprise. That this Hopf manifolds that you realize as a quotient of an abelian group acting on the CN, this cannabis abelian, you can realize it with more symmetry. Actually, on CN, there is the standard representation of SLN. Just matrix multiplication, so SLN active of standard way on CN. So sorry. SLN from CN. And this XD, you can realize this as an homogeneous space of SLN. By okay, so an HT, so it's not system a gamma D. And the thing is that when you take the normalizer of this HT within an SLN, you get a flat manifold. So for those, you know, in other words, this is a parabolic subgroup of SN. So you have a fixation of your Hopf manifold with fiber. So this normalizer model by HT is a compact torus. But you have realized, this is why I said I will bring more of geometry, more of the symmetry. This Hopf manifold is actually a SLN homogeneous space. And this fiber over something algebraic, a flat manifold. And this fibration is carries a universality property among all. So this is an homogeneous space which is compact. This one is compact. And this one is non-Keller. Because there is a famous result, let's say, I will say that this is the geometric Hits bundle. Whenever you have an homogeneous space under a collective complex Lie group, collective is important. This given homogeneous space is scalar if and only if it is a flat manifold. So here you see if you now, so here you are in the case of the Hopf manifold. So you can drop this assumption of homogeneous under SLN and ask for any image. Fibering over a flat manifold, that are people P because these P are generalized, they are parabolic subgroup. But let's, as I said, if you don't know this, just say that this is a flat manifold. for any G, let's, here I will put some word on the presentation of theory, so I will not only with this topological things connected, but I will demand this to be I will demand this be reductive, meaning that, okay, not meaning, but implying that the representation theory is nice. Let me just. Also, this is a conference on representation theories. I will not explain this. So this give you, these guys, they are not field. So this is known. These are, now we have two bunch of two nice non-Kähler compact complex manifolds, the LVMB manifold, and this homogeneous guy. So for sure, if you take this very simple, so let me go on with observation. So we are now on the situation we only observe. What can you do? And how can you build from these two classes? One for the class of non-Kähler compact complex manifold, you just take fiber products. Maybe and you get for sure further complex, further non-Kähler complex manifold. But the step that you have made is not that wonderful. So let's do something but at least kind of observe this. So I would like to generalize this picture. What I'm going to do now. So I'm dealing with this. How will you use this? So, in the Bosio case, you see, okay, so there is a geometry here, CN is a file space. I will regard CN now as a module, but as a module which is trivial. And I said I want to go on with further groups, let's say non-Abelian group action. Okay, I have to look at my notes if I want to be concise, very concise even. So what we are given? So we are given a bit more. So as I said, the G is before the connected, connected LUT algebraical. This is given. I have the black manifold, so it's nice. So group P parabolic. We want to have this. Black manifold. So it is projective if you want. And now there is a nice here from the geometry, but the geometry we translated in representation of theory. If you look at the Picard group of P, so this is an example of geometrical representation theory, you can realize any light bundle, their character as we saw in Rita. So you can get some point. Just take the character and take this light bundle of C. Whenever P after C by this character, so I like to put a key. Like this. You have this. So now this Picard group has a nice basis. So now you regard them as a light bundle, but prime divisors. Sorry, classes of divisors. And there is a nice basis, the so-called Schubert divisors. This is a basis on this. Basis. That's it. You are an affiliation, so let's say you have S on them. And thanks to with this divisor. So this is completely so now what I'm doing here, once you know this, so then this divisor set to the characterization, and they are given by character, three fundamental weights, keep if you want. And if you take the presentation of theory, when you take global section of this time version, given by this RPJ, they are, I'm saying because I will put the dual, this carries a natural G module structure, and they are irreducible G module structure. Irreducible G module. As usual, avec INF, so la IO-Suite module is IO-Suite. So let me write them as usual like that. Now here is the theorem. One of our students, so this is not a Pierre Brogolier. Post this mix. Give my talk. Another audience. One more talk on this. Another audience which is more algebraic. I did it 2 days ago in a complex of people complex manifold knowing anything about representation theory. So each time is I am struggling with the audience. Yeah. So what you are given? So you are given this function data. Even more. So like with the Battisti Rosio case, I mean, I will not have solid classification for the moment. I will just give you this bunch of data. So what you are given now, so this lattice, this sorry, in the toric case, I mean, this is a lattice and this is the co-character lattice of an algebraic torus. So what is the pendant of the algebraic torus? Here we are not working algebraic torus anymore, but we are working with this parabolic subgroup. So we are taking a lattice in, and this is the idea. To take a quasi-lattice, a finite generated Abelian group is in the character, in the verification, no, the real span of the character of P. I read this information. And yeah, finitely generated Abelian. So a fun, but now I have where I am taking, I want to take my action. Okay, so Boson, this is a CN, a module you can regard as a CN, but we put more structure. So I need a module. I will want to here. So I'm taking now the sum of all this, yes, was not image, all this irreducible module. This will be my module. And then we have polar fan, so we not explain everything, but the fan again. Supported. When you do toric geometry of these control things, you are not working on the character, but then I say not the co-character of the algebraic torus. Here, it will be the co-character of P, which are given by co-root, let's say. And I'm taking the one which are joined to the omega j, so this, so the back pj. So this will be the co-sequence rule, so to say. Like this. Okay. And this collapsing, this is already a fan, but in this file, supported on this, supported on, sorry, on the N, on N. So on N, what is this N? This is polarities. Okay, so this link is okay. I have that. So I have a fan, but I want to, I have some rays, and I want to keep track of the rays which hit the co-simple roots. So this additional piece of that tool will tell me whether rays, so I want to write it, rays of my fan are given by co-simple roots. So this is the input, the idea. So now I have an epimorphism. Rho, c'est rho, pardon, c'est pas la F, the rays of my fan, so color fan function. The rays of my fan in this very end. Maybe no, I don't need it. This is what I said in the color of what colors means. I said it in what you even any such function like that. There exists a U that I can express. This is a heuristic here, or I can attach to the very fine unit, same way as this here goes you, a fine, an open subset, but where? Where? So this will not be only the module I want to look at. I want to look at, this is why I need it. Not only in this very V, but a V with this Cn of Bosio, but this Cn that I regard as G module, so this will be trivial module, and copy of it. I regard this, so I expand this, so here I have this function, this Bosio part, regarding as a G module with this this is a trivial G module, so I have over time, let me give, can I have 2 minutes to finish? Yes. Okay. But I want to be even more precise. So, okay. So where do I live especially? I live in the relative spectrum of the cross-ring of this flag variety. This is just this guy, the total coordinate ring. You take all divide, pick up line bundle, all the last section, but only this one. Okay, so this will be my non-abelian and the Bosio part. And this is a nice variety. It is called a spherical variety. It is a generalization to the non-abelian case topic. So G acts and acts. And we have also the Bosio action. These two actions commute. So now you can talk about the quotient. So as a Nordic space, not fancy GRT quotient, but this very CM action, because what is the Bosio action now? And here is also the idea. So you see, there was this linear form. So now I decompose each copies of C in this piece Cn. So now I'm taking this very decomposition of Bosio, and then each irreducible segment I have the LG. On the wall, here for Bosio, the pieces were trivial module, but here my pieces are irreducible modules. The generalization. So now this is, as I said, I have two actions. So Bosio action and this G action, and I regard this up to CM action, so Bosio action, and this is the action is proper, it is continuous and free, so I will get a compact complex manifold. Because I have two actions which commute, this action of G distant, so I have a G variety, a G manifold, which is not necessarily homogeneous in general, it's not, This is a generalization of the Hopf manifold, and it is not theory. And here, contrary to both to Mersmann and Bosio, which proves the non-reliability by this cohomological substitution condition here, I don't need this cohomology because I have this G action. This guy is compact, and I'm considering the closed orbit of it. This closed orbit, if this manifold were from a Keller, every submanifold of it will be also Keller. So in particular, the closed orbit will be Keller. And as we quote, the compact homogeneous spaces which are Keller are flag manifolds. And definitely here, these are not flag. So this is really purely symmetry here that I am using. Now this is done with the Tobias rate. And I said I will focus on the construction, so I have done construction, and after now the story begins with a lot of questions. So for instance, why have this generalization of Katzka conducts to Berchowski-Mersmann? Yes, this is what I'm doing now. So I will not call this, I'm sorry, but quantum spherical stacks. Because quantum, as we see from presentations, for me is really misleading. So I will have an analytic space with the G action. Now I will have to look at its shifts and see whether I can say something about story presentation theory. And whenever this is a lattice, in this case, when I find a supportive of the lattice, I have to get the variety, which is also complete. These are the so-called spherical varieties. They are generalizes the deconchini compactification, even compactification of symmetric spaces. I think it's very nice. Thank you.
Very interesting fact. Any questions?
Do you know in the last argument you mentioned that you can recognize the complex orbits in this space.
Yeah.
So
yeah,
you can recognize that they're not like manifolds, but can you find them among the fixed manifolds or something? Yeah.
Whether what?
Well, these fixed vibrations.
Yeah.
So can you identify which fixed vibrations you get?
Yes, whenever I'm kind of supported on the lattice, I have also this picture. This will be this spherical. This is as a G variety. So here it is complete. This variety not necessarily projective. So I have this is the G variety. So I have flag manifolds, not on G mod P, G mod P prime, 2 if you want. And here I have also a G mod H, and with this sticks vibration there. So if you want, you can regard, so here we have compactification of compact homogeneous space, of homogeneous space, whose subgroup here actually, whose algebraic closure is an algebraic group here. That we don't explain. Thank you, features. So, I mean, those no here for people with that. I mean, this is the non-aggregate version of what I say.
More questions? If not, then thanks for the